this lesson, we're going to learn about tangent, secants, and chords and the angles that are formed by those in circles. So the first thing here is the definition of a tangent line. So a tangent line is a line or part of a line that intersects a circle in exactly one point. So if I look at this picture here, let me just fix these letters so that you can see them better. So if I look at this picture, I'm looking for a line or part of a line that intersects the circle in one place. And that's going to be this line right here that intersects the circle at point C. So point C is called the point of tangency. And if I want to just give an example of the tangent line, well, I'm going to name this line CD because that's the 2 points it passes through. The next segment or line to talk about is a secant. So a secant is a line or part of a line that intersects a circle in 2 points. So if we look at the example of that, that would be this blue line because that's intersecting the circle at point B and at point E. So this is EB, or line EB would be a secant. And notice, I'm going to actually go back and highlight this. A line or part of a line and a tangent is a line or part of a line. But then when I get to the next one, which is a chord has to be a segment. So it has to have endpoints that are on the circle, meaning it's going to intersect the circle in 2 places, but that's where the endpoints go. So there's several examples of chords in this picture. AC is an example. The diameter is always going to be a chord. So AOB, or you could just say AB is a chord. And then another example would be EB or BE. Are also chords. So these are all chords because they are segments whose endpoints are on the circle. So now let's look at the angles that are formed by these different types of segments or lines. So the first type we're going to look at are what we're going to call them as on angles, or meaning their vertex is on the circle. So there's some different situations. The first one you've already seen, an inscribed angle. So an inscribed angle, remember the vertex is on the circle, but the angle is completely contained in the circle, and it's formed by 2 intersecting chords. So if you recall, the formula for this is that the angle is always 1/2 of its intercepted arc. So if I have my angle here, the arc that it cuts into is this 100-degree arc. This angle will be half of that. It's just going to be 50. So my angle, x, is equal to 1/2 of the 100. So I get x equals 50. If I look at the next scenario here, it's a tangent chord angle. So a tangent chord angle means that you have a tangent. So this segment right here is a tangent because it's intersecting the circle at point B, so only in one place. And then this portion is a chord because its endpoints are on this circle. So if I look at the arc that it cuts into, it's actually cutting into this entire arc right here. But because the vertex is on the circle, the formula for this is still going to be that the angle is 1/2 of the arc. So that means x will be 1/2 of the 120, which means x is going to be 60. So notice how these formulas are the same. It's because the vertex is located in that same position. It's on the circle. Even though we started with 2 chords versus a chord and a tangent, the formula will still be the same. So let's go ahead and look at this next example where you have a tangent and a radius. So in this particular problem, you have a tangent line, again, intersecting the circle in one place, and you have a radius. Now for radius, if you remember in a circle, all radii are the same. So if this is a radius, and if I extend this down and draw in the other radius, well, that means really you have a diameter. So a diameter in a tangent or a radius in a tangent. If you look at the way that this cuts into the circle, so let me just go ahead and extend this. It's cutting into the circle, depending on which side you're looking at, you see 2 semi-circles that are formed. So basically this right here would be your intercepted arc if I was looking at this angle, or you could look at the other side and say, well, this is your intercepted arc. And no matter what, this arc right here is 180 degrees, so this angle has to be 90 because the vertex is on the circle, so the angle is always going to be 1/2 of the intercepted arc. So that's why this is going to be 90. So in this case, I'm just going to make a little note here that tangents are perpendicular to radii. Or you could say tangents are perpendicular to diameters. Same idea, but that's an important thing to know. It's really a theorem, but it applies here because the vertex of this angle is still on the circle. So I'm going to just make sure you see the formula as well. The angle equals 1/2 the arc. Well, the angle has to be half of the semicircle, which was 180 degrees. So that's why the angle has to be 90, forming the perpendicular lines. So in summary, whenever the vertex is on the circle, notice we're using that same formula. The angle is 1/2 of the arc. So the next type of angle we're going to talk about is when we move the vertex outside of the circle. So there's some different types of situations that can occur for this. You can have angles that are formed by two tangents. So taking two tangents right here, and these are tangents because they're intersecting the circle in one spot. Notice that the vertex is located outside of the circle. So since the vertex is located outside of the circle, we have to change up our formula a little bit. So I have where this angle is cutting into the circle, it's really exposing the entire circle. So we have this big arc, which we call the major arc because it's the larger arc. And then this arc right here that you see from where the angle intersects, that's called the minor arc because it's the smaller of the two arcs. It's less than the 180, so that's why we call it minor versus major is greater than 180. So when I look at the formula here, the measure of this angle is going to be 1/2 the difference of these arcs. So I'm going to just so it's right here, but I'm going to just shorten it up using the same kind of formula that I talked about earlier. So the angle, not arc, the angle is equal to 1/2, and I'm just going to say arc 1 minus arc 2, meaning, or you could write big arc minus small arc if you want, but you should know to do the bigger arc minus the smaller arc. So when I look at this, the vertex is located outside of the circle. What I'm going to do is the angle, which is going to be x, is equal to 1/2. So the big arc minus the small arc. Just going to double check that that was 100. Yep. So when I do that, I am going to simplify inside the parentheses. So x equals 1/2 of 160. So that means x is going to equal 80. So this formula will also apply to this next picture because if you look at where this vertex is, it's outside of the circle, just like this vertex B. It was outside of the circle. So since the vertex is outside of the circle, my formula is going to be 1/2 arc 1 minus arc 2. Notice the situation's different. This time we're talking about taking two secants. So look at where your angle is. It's two secants. They're intersecting the circle in two places, but they extend outside of the circle, so they're secants. If you look at your intercepted arcs, well, you have this arc in front where the angle cuts into the circle, but then you also have this little section right here. So those are the two intercepted arcs. So when I go to actually solve this, x is going to equal 1/2, so the big arc, so 80, minus the small arc. So x equals 1/2, 60. So it's going to equal 30 degrees. So same formula, two different types of segments that are intersecting, but because the vertex was located on the outside, same formula. So continue to the next page here. And we see, again, another situation where the vertex is located outside of the circle. So if you can guess, the formula is going to be the same. We're going to do the angle is going to equal 1/2 the difference of the arcs. This scenario was created by a tangent and a secant, but again, that vertex tells us everything. So if we go to highlight this angle, Here's your tangent because it's intersecting in one spot. Secant intersecting in two places. Look at the arcs that it cuts into. It cuts into this 100-degree arc, and then it cuts into the 30-degree arc. So those are my two arcs that I'm going to be using. So x will be equal to 1/2 the major arc minus the minor arc. So x will be 1/2 of 70, which is 35. So that's how I'm getting that one. So then the next type, so we've talked about angles that are the vertex is on the circle, outside of the circle. The next one is what happens if it's in the circle. So there's two different scenarios to talk about for this. One of them is it's just located anywhere in the circle. So let me go ahead and highlight. So this one, the vertex is inside of the circle anywhere but the center, versus the vertex is in the center of the circle. So we have anywhere in the circle is formed by two chords. And if you look at the formula, you're finding the average of the arcs that the angle cuts into. So let's go ahead and just highlight this for a second. If I have angle X, which is what I'm trying to find, hopefully you're looking at this and thinking vertical angles are formed. So these two angles have to be congruent. So if you look at the arcs that those two angles cut into, what you have to do is find the average of those because they're equal to each other. So I look at the arc that's in front of X. Oops, let me zoom back in here. And then if I look at the arc that's behind X, or in front of its vertical angle, because these two are congruent, those are the two arcs that I need to use. So I need to find the average of those since the angles are equal. So that's where this formula comes from. The angle is going to be equal to 1/2 the sum of the two arcs. And when you add the two arcs, it's not going to matter how you add them because you're just adding. So in this case, X will be equal to 1/2 of 170 plus 70. So X is going to be equal to 1/2 of 240, which will give me 120. So each of those vertical angles has to equal 120. The last situation is one that you've already learned about, and this is the easiest of all of them, and it's because the vertex is on the center of the circle. So remember, there's in the circle in this previous example, but not on the center, and then there's in the circle where it's on the center. And for this situation, you look at the arc that this angle intercepts, and the angle is always equal to that arc. So that's the easiest situation. So the angle is equal to the arc. So in this case, X is just going to equal 80. This is going to be formed with two radii. You could also extend these and have chords or diameters that are intersecting, but the main thing is where that vertex is located. If it's in the center, or on the center, I should say, then the angle is equal to that arc. So in this case, we call this a central angle. So I've talked about a lot of different formulas. So what I want to do is just summarize these in a chart for you. So we have our center of the circle is where the vertex is located. So I usually call, when I talk about these, I'm going to say, okay, they're center angles, meaning they're located on the center. So that's this picture right here. This was a center angle. The vertex, it's really called a central angle, but the vertex is located on the center. So in this case, the angle is equal to the arc. Then we had inside the circle, but not on the center. So I call these, let me get back to that page, I call these in angles, meaning the vertex is in the circle but not on the center. So this is, the angle is going to be equal to 1/2 the sum of the two arcs. So this is when you have the X, or the vertical angles. So I call these the in angles if I go back and label. And you have to do the average because you have the vertical angles. The next type I call out angles, meaning the vertex is outside of the circle. So we saw that at the top of this page, but we also saw it on the previous page. So I'm going to just label that section. So this I call out angles. And then while I'm here, this other section I call on angles because the vertex is on. So I'm going to just fill that in the chart. So out angles, or vertices outside of the circle, you have to do the difference. So 1/2 the difference of the angles, or of the arcs. So remember, big arc minus small arc. And then for on angles, this is the angle is equal to 1/2 of the arc. And one of the scenarios that we did not talk about for on angles, so I'm just going to sketch a picture so it says what is the exception to this rule for on angles. We didn't consider a situation where you have a chord and a secant. So something like this. So in this picture, we have a secant, that purple line right there that's crossing through, and we have a chord. This does not follow the on rule because of the fact that if you look at this angle right here, part of it is outside of the circle. Versus if this was a tangent line, then we can use the on rule because the line is going right up next to the circle, so the angle is contained inside. So we have the chord and then we have that tangent. But in this particular problem, since we have this chord, this portion is in the circle, but then we have this other little section that goes outside of the circle, you have to say that this does not follow on. So I'm just going to do a little note here. The angle does not equal 1/2 the arc. So you'd have to use other methods to figure that out. So just be aware of that. So this is when you have a chord and a secant angle. The rule is not followed. So that's the exception. So just be aware of that. It does exist. It's not something that you'll see very often, but it does exist. Otherwise, you're safe to say follow these. Where's the location of the vertex? And that really tells you the formula to use. So go ahead, get some key ideas written down, and then do the check your understanding problems.